Hi students, this is a review video for the force and friction test that you will have coming up soon. Listed here are the different problems or different types of problems that we're going to have on the test. So the first one is force problems, then we have weight problems, force upwards problems, meaning throwing an object or shooting a rocket up, hanging mass problems, friction problems, and a few acceleration problems. A few, meaning there's going to be 3 to 4 of them, and they're going to be the hard set, the ones that build off of each other. So those last 3 where, first you have to calculate the acceleration and then solve for the distance, then you need to figure out how fast an object is going to be going from that rate of acceleration. So that should be relatively easy since we've done so many of them. It's just keeping it fresh before the midterm. I'm going to go through these different types of problems and how we solve them and review a couple equations that will help you. So the 2 big equations, and really they're kind of the same thing, is net force is equal to the force being placed on the object to accelerate it at whatever the desired rate is, plus the force of gravity. Now that object could be a box, that object could be a rocket, who knows. The other one, which is basically the same thing, is the net force, or the total force, is equal to the force on the object plus the force of friction. So what we're seeing with both of these equations is that we need to account for how quickly we want the object to accelerate, and then we need to account for whatever the opposing force is going to be, either the force of gravity or the force of friction, and that will tell us the total force or the net force that is required to accelerate that object. So this brings us to force upwards problems. These relate to holding an item, throwing an item, or rockets. So let's just start with a little drawing. Here is a person who is holding a box. If this box is 10 kilograms in mass, and we're just talking about holding that item, right? Holding it takes force. Holding it out there and keeping it at that height requires force. The force that we are fighting is the downward force of gravity. The force of gravity will be the 10 kilograms times the 10 meters per second squared. So we know that it takes 100 newtons just to hold that object there. If we're then going to take that same 10 kilogram object and not just fight the force of gravity, but we also want to toss it up in the air at 5 meters per second squared. Tossing it alone, if there was no gravity, if we were out in space, would require you to take, so the force of the object is going to be 10 kilograms times the 5 meters per second, and you end up with, that should be a circle, and we should end up with 50 newtons. So we now require 100 newtons just to hold the object and 50 newtons to throw the object. So that means that in total, our net force, if we're coming back to this equation, the force of the object plus the force of gravity equals the net force, or the total force that's going to be exerted on it, will be 150 newtons. So in both of these examples here, we've had to deal with the force of gravity, how much force it takes just to hold the object up before we even throw it. If we were on the moon, where the moon's acceleration due to gravity is 1.6 instead of 10, we would replace 10 with 1.6, and that would then, of course, influence this number as well, right? This is no different than a rocket problem. Rather than thinking about an object that we're throwing up into the air, when you have a rocket and it's 10 kilograms, here's our little rocket, it's going to blast off into space. If we want to accelerate it upwards at 5 meters per second squared, and the acceleration due to gravity is coming down at 10 meters per second squared, if we need to figure out how much force is going to be required to accelerate it that quickly, we need to account for You guessed it, the force of gravity. We can do that in one of two ways. We can deal with it in terms of forces, or we can deal with it in terms of accelerations. So just like we did over here, we can say the 10 kilogram object times 10 meters per second squared equals 100 newtons. That deals with force of gravity. We can also take the 10 kilograms times the 5 meters per second squared, and that deals with 50 newtons to shoot the rocket upwards if gravity wasn't there. Account for them both, we've got 150 newtons. An easier way, in my opinion, is to take the 10 kg and multiply it by 5 plus 10, the two like terms, 5 meters per second squared and 10 meters per second squared. Gets you the same 150 newtons. So in all of these three problems so far, we have been using this idea here, and we have been solving for the net force. It is just as possible to be given the net force, right? Here's the amount of force that the rocket has. We often call that thrust, right? So net force, it's also known as total force, or thrust if you're talking about rockets. It could also be just like the push, right? How much to push or to throw, how much force you have available. You can know that number and then solve for the force of the object, right? You can be given the mass of it, or you can be given the acceleration. So let's do one of those. Let's say that I'm here, let's say that I have 100 newtons, and I'm going to throw this 5 kilogram box. How quickly will it accelerate with 100 newtons of net force? That's the total force that I have to throw this object. If I've got 100 newtons and I'm going to throw this 5 kilogram object, the first thing that I have to count for is the downward force of gravity. So we know that the downward force of gravity is going to equal to 5 kilograms times 10 meters per second squared, 50 newtons of force of gravity. So if we come back to this equation, net force equals force of object plus force of gravity, we can say 100N equals 50N plus whatever is left over is the force that will actually be exerted on the object to get it to move. We subtract, you're left with 50 newtons equals the force being placed on the object. If we know it's a 5 kilogram object, divide by 5 to figure out the rate of acceleration, which would be 10 meters per second squared. Right? If instead we didn't know what this was, but we knew what the rate of acceleration was, we could also solve for those problems just in different variables, right? No matter what, we know with this net force equation, we know if we're going to write this differently, if net force, which is F equals m times A, is going to equal the force of the object, F equals m times A, and the force of gravity, which is going to be F equals m times 10, assuming we're on Earth, right? If we know what the mass is, then we can fill mass in all of these places. If we know what the force is, or the total net force, we can fill that in. If we know how quickly it ends up accelerating, we can fill that in, right? So we know we've got lots of variables here that we can start filling things in for. But the idea, when we're talking about throwing an object in the air, whether that's a rocket, whether that's a box, is that we need to not only account for the force that it would take to accelerate the object without gravity, but we also need to deal with gravity. So since I have to overcome gravity, I'm going to add those two forces together to figure out my total force. If I know my total force, then I'm going to subtract the force of gravity from there to figure out my force of object. So we're moving on now down to friction problems. These are pretty much exactly the same, right? If we have a table here, and we've got an object on the table, there's going to be friction right there between the two surfaces. So if I push that object, if I apply a force with 50 newtons, but there's 40 newtons of friction, how much force is actually left over after we've dealt with the friction? Well, that tells us that we're going to end up with 10 newtons. Now, how did I get that? If this is the push, that is the net force that I have available to me. So I'm going to say 50 newtons is equal to the friction, 40N, plus however much force will be left over to accelerate the object. So we're going to subtract 40 from both sides, and we're left over with that 10 newtons of force is my force of object. Meaning that's the force that will actually be acting on the object. If we just say, for make the math simple, it's 1 kilogram, then we know that it will accelerate at 10 meters per second squared, right? 10N equals 1 kg times our acceleration, divide both sides by 1, our acceleration is 10 meters per second squared. In other cases, we are solving, just like we were up in these other problems, rather than solving for the force of the object, how much is placed onto the object, maybe we're told, okay, you want it to accelerate at a certain rate, and, here I'm going to erase some of this stuff so we've got more room. So it's erased. If, once again, we've got the table, we've got the block on the table, maybe we're told how much friction there is. There is 10 newtons of friction. Despite that friction, we want this 1 kilogram object to accelerate, despite the friction, at 10 meters per second squared. So the way that we need to think about this is just like how we think about it when we're dealing with gravity and we're dealing with throwing an object. I not only need to figure out how much force is required to move that object, but I also need to account for friction. So I need to say we've got the force of the object plus the force of friction. So that means that I need to take, and that'll equal how much total force is required. So the force of the object is going to be that 1 kilogram times 10 meters per second squared. The force of friction is going to be what's given to us, 10 newtons. So I know that I need to provide a total force of 20 newtons. 1 times 10 is 10 newtons. We add those two together. Because I not only have to push the object in a frictionless world, right? If I was on ice or a purely frictionless surface, I could just push that object with 10 newtons and it would accelerate at 10 meters per second squared. But we have to deal with friction. There's a lot of friction between that object and the table. Maybe it's a sandpaper table, right? So there's a lot of friction. So when I push it, I have to add the amount of force that I want, or that I'm required to push the object with. Which once again brings us back to this equation. And we're again seeing time and time again how these two equations are exactly the same. All we're saying is the total force that is required to push an object with is how much force it would require to move that object without gravity or friction, and then we just need to account for gravity or friction. Right? Meaning, gravity and friction both oppose motion. Gravity slows down motion when we're trying to move straight up. Friction slows down motion when we're trying to move something sideways. So if I want the object to accelerate at a certain rate, I need to push harder because friction is there. We can think of friction as somebody that's holding on to the back of your jacket while you're trying to run. Right? If you're trying to run, you might be able to sprint really quickly. But as soon as somebody grabs onto that jacket, you're going to have to work even harder to keep moving at the same pace that you were moving before. That's the exact same way that friction and gravity work. You need to work harder or push harder in order to account for gravity and to account for friction, which is why we are going to add the amount of force to figure out our total net force. Similarly, we can reverse that. We can be given the net force, we know the friction or we know the gravity, and then we can figure out how heavy the object is or how fast it accelerates. So hanging problems, hopefully by now these are relatively simple. These all have to do with gravity. So here's my drawing of the example, right? So you've got one box here, you've got another box up here. We're assuming that this is a frictionless surface. Right? So we can be solving for the acceleration. We can be solving for the acceleration of this block. We could be solving for the mass of this block. Or, theoretically, we could be solving for the acceleration or mass of this block if we know certain things about the other one. So for instance, if we know that this block is 10 kilograms, we know that the force of gravity pulling down on it will accelerate at 10 meters per second squared. So there's 100 newtons of force pulling on this box. If it's pulling down on this box, it's going to pull from this string, which is then going to pull on this block. So if we know its mass, 5 kilograms, we can figure out how quickly it'll accelerate. 100 divided by 5 would be 20. If, instead, we knew that this block is going to accelerate at 20 meters per second squared, we could figure out its mass. 100 divided by 20 equals 5. In a different scenario, if we know how heavy this block is and how quickly it accelerates, we know the amount of force that it is moving with. 10 times 20 is going to give us 200 newtons. If this block is moving with 200 newtons, that means that there must be 200 newtons pulling on this block right here. If there's 200 newtons pulling on it, and the only force pulling on it is gravity, 10 meters per second squared, we could solve for its mass. 200 divided by 10 is going to be 20 kg. So we can also solve for the mass that goes in here. So with the hanging problems, really the important thing that we have to remember here is that whatever force we're dealing with is the force of gravity. So by that I mean that we just need to always keep in mind that the force that's going to be pulling down on this block is going to be accelerating it at 10 meters per second squared. Right? If you remember that, then you can go through and solve based on whatever variables you do or do not know. If you know the mass here, you just multiply these two things. If you know the mass here and the acceleration, you can then end up dividing, right? You just need to be very methodical about it, and I would draw things out, right? All too often, the problem that we see, whether we're dealing with hanging problems or whether we are dealing with friction or rockets, is that people don't actually take the time to draw out the rocket, to draw out the block sliding across the table, to draw the person throwing the object, or to label what different forces and accelerations are occurring in different places. If you draw pictures and you label, there's a greater likelihood that you'll be thinking of the whole system, right? That you'll be thinking of the gravity or the friction, you'll be thinking of the object and the total force acting on that object.